Autonomous mobile robots have achieved significant success in real-world applications such as object reconstruction and environment exploration. In these applications, it is crucial to identify the most informative view for taking measurements, which is known as the next best view problem, and an informative path to reach the selected view. In this work, we focus on how the robot should move between NBVs to maximize object coverage. Current methods often rely on sampling-based path planning techniques, which are computationally expensive because they require evaluating numerous candidate views along the path. To this end, we propose a computationally efficient solution that enables the robot to focus on unknown regions while moving to the next best view. Our main contributions are as follows. We propose a computationally efficient method to provide comparable object coverage and entropy performance to the state-of-the-art while significantly decreasing the computation time. Our proposed approach for increasing object coverage while moving between NBVs does not require fixed candidate views along the path for evaluation. We simplify the task by freeing up 1 degree of freedom. To achieve this, we propose a control strategy that considers only the camera position and direction, rather than its pose. Given the partial object model and the view candidates generated on a cylinder around it, we use an existing algorithm to estimate the next best view. Our work focuses on how the robot should move between next best views to maximize object coverage. To this end, we propose an Object-Reconstruction-Aware control strategy that includes a raycasting-based focus point estimation method, which enables the robot to focus on unknown regions, and a whole-body control strategy that ensures coordinated motion toward the target next best view while keeping the focus point within the camera's field of view and avoiding collisions with obstacles in the environment. Since our method does not rely on sampling intermediate views, it is computationally efficient. Let's suppose the robot maintains the current focus point within the camera's field of view while moving to the next best view. Once the robot has traveled sufficiently far, a new focus point is computed, as the previously unknown region has become known to the robot. To determine a new focus point, we create a virtual field of view facing the center of the search space cylinder to focus on areas near the object. We compute a focus point that helps the robot reveal more unknown area while traveling to the next best view. To do this, we cast rays from the camera center and evaluate each ray using entropy along the ray. We select the ray with maximum entropy as the best ray and place a focus point on it. Keeping this point within the camera field of view directs the robot toward informative, unknown areas. After calculating the new focus point, the visibility constraint guides the robot to keep it within the camera's field of view. The robot maintains this point until it either determines a new focus point or reaches the next best view. We formulate the control problem as a quadratic program with linear constraints that generates control velocities for the robot. The objective function consists of error dynamics for reaching the target position and direction, as well as a term that minimizes the control variables. We include linear constraints to avoid collisions and mitigate local minima through circulation. We also limit the robot's velocities and joint angles. Finally, we use a soft visibility constraint to keep the focus point within the camera's field of view. We used following 3 strategies while the robot moves between NBVs during the experiments. Focus. The robot keeps an informative focus point inside the camera field of view using our proposed method. Sampling. The robot uses an RRT star sampling-based method to plan an informative path. No path. The robot moves toward the NBV without focusing on any particular point. The experimental setup contains a blue rectangular object for reconstruction. A virtual cylinder prevents collisions between the robot and the object under reconstruction. The robot has an omnidirectional base and a 5 degree of freedom robotic arm, and measurements are taken by a depth camera attached to the end effector. We use OptiTrack system and tracking markers to continuously track the robot's pose. Finally, for circular obstacles are placed in the environment. We first present the reconstruction videos of the three methods individually until the first next best view to illustrate the robot motions at their original speeds. The first NBV and focus point are determined. The robot moves toward the NBV while focusing on the focus point. It avoids the obstacle and circulates around it. Once the robot has moved far enough, a new focus point is calculated. The robot stops focusing on the focus point to prioritize reaching the NBV. The first NBV and shortest path nodes, which are shown as green spheres, are calculated. Random views are sampled around the node, and the one revealing the most unknown area is selected as the best view sample. The robot visits the selected view, and a new view is calculated around the next shortest path node as before. The robot moves to the next best view without keeping any focus point in the camera's field of view or visiting intermediate view samples. Its sole purpose is to reach the NBV. We present the reconstruction videos of the three methods at 8 times the original speed to facilitate visual comparison of the robot motion and the online object reconstruction process for the remaining next best view. Focus and no-path methods have finished the reconstruction process, while the sampling method continues. We measured following metrics during the experiments. Covered volume, the sum of occupied and free volume. Entropy, the entropy in the bounding box surrounding the object. Time, the time that the robot spends traveling between NBVs. Considering covered volume, the sampling method and our method, focus, increase the covered volume much faster than the no-path baseline. A similar trend to covered volume appears in the entropy metric, as entropy reduction under the focus and sampling strategies is significantly faster. Finally, considering the time metric, our method requires significantly less computation time than the sampling method, without increasing the time compared to no path. We conducted a second experiment using only our focus method to demonstrate the generalizability of the proposed approach. In this experiment, we use a legged manipulator. Robot body and end effector are represented by spheres. We define a virtual cylinder to prevent the robot from entering the object area. Finally, we use 4 plane constraints to prevent the robot from hitting the workspace walls. The first and second rows illustrate the reconstruction operation for the barrier and chair objects using our focus point method. We present reconstruction videos of 3 methods in simulation at 4 times the original speed. We present the obstacle avoidance performance in a cluttered environment, where the robot performs a reconstruction task using our method. The robot keeps the focus point within the camera field of view while avoiding obstacles and circulating around them.